striking difference between linear and nonlinear oscillators. And that difference is in the dependence of the frequency on the initial displacement. For the linear oscillator, and here is a linear oscillator, there is no dependence. The frequency is independent of the initial amplitude. But for the nonlinear oscillator, and here's an example of a nonlinear oscillator, there is a dependence of the frequency on the initial displacement. And that took a long time to sink into my head, that fundamental difference. You can see the independence in the case of the linear oscillator because you can write down the solution in closed form and you can graph the solution and study it analytically and so forth. But for the nonlinear oscillator, there is no closed form solution in general. So to study the dependence of the frequency on the initial amplitude for the nonlinear oscillator, various analytic approximations are used, and typically a Lindstedt perturbation is used. Recently, Maple added a command for generating that kind of a perturbation expansion. Didn't have that years ago. It's there now. It's in the Student ODEs package, and it has inherited the ability to provide the steps of a calculation. In fact, in example 8 in this particular webinar, which I did not so long ago, there's in that example the syntax-free way of generating that stepwise solution in the Student ODEs package is discussed. So in today's webinar, we want to look at this functionality of the Lindstedt perturbation in greater detail. And for greater insight, we're also going to obtain the expansion without using the Student ODE package, using Maple commands at a top level. So we're going to end up with an analytic and visual evidence of the dependence of the frequency on the initial amplitude for this nonlinear oscillator. Let's initialize this worksheet. I'm going to need something from the plots package and the Student ODEs package. We need the linear oscillator, the nonlinear oscillator, and the initial conditions. Let's take a look at the linear oscillator. Equation, initial conditions, use dsolve, and here's the analytic solution. You can just see from this expression that the frequency is not going to depend on the amplitude. Here's a graph. Black curve is cos pi t. Red curve is 2 cos pi t, which is what would happen if you change a from 1 to 2. And you'll notice that the period is independent of the initial amplitude. They both have different initial amplitudes, but the frequencies are the same. And here I'm just clarifying frequency, period, and angular frequency. Next, we want to look at this thing called the regular perturbation, and it has a shortcoming. So, regular perturbation solution for this initial value problem. X double dot, X dot, X. Linear oscillator dependent on this particular parameter, A. The regular perturbation assumes a solution of the form in multiples or powers of the parameter a. This is typically called an x0. This would be called an x1. The next term would be a squared x2. But I only need these two terms to show what I want to show, so I call them u and v. You take that expression, take its second derivative. Here you take its first derivative, and here you don't take any derivatives at all. You collect powers of a, u double dot here, u here. So this is the coefficient of a to the 0. This is the coefficient of a to the first power, coefficient of a to the second power. Let's solve for u by assuming that each of these coefficients separately must vanish. So you get u double dot plus u equals 0. Here are the initial conditions applied to u. Solution of this initial value problem is u equals cos t. You then turn your attention to the initial value problem you get when you set this coefficient equal to 0. And you notice this coefficient has a u dot. So you need the solution for u before you can get the solution for v. So v double dot 2u dot v, and u dot is minus sine t, and then this becomes the initial value problem you need to solve. The initial conditions now are the inert initial conditions for v, and if you think about this, you get v double dot and v. That forms the homogeneous part of the differential equation, and this becomes the driving term. The homogeneous equation is going to contain a sine t and a cosine t, but the initial conditions will take care of which one drops out. But this sine t here in a particular solution means you pick up a t cosine t, and this term becomes unbounded as t increases. You get oscillations that get bigger and bigger. Means that this regular perturbation is not very useful. These terms are called secular terms, and some means has to be devised to solve the oscillator problems in nonlinear cases where a regular perturbation would give these secular terms, but the thought that the frequency depends on the initial amplitude changes what you can do. Let's now turn our attention to the nonlinear oscillator. And we're going to begin by just hitting it with this Lindstedt expansion command, Lindstedt perturbation command, that's in the Student ODEs package. Now, the Student ODEs package has already been installed, right? Student ODEs. This solve is a sub package, and by perturbation is a command in this sub package. You give it the differential equation, the initial conditions, the unknown that you're solving for, the parameter, and the order of the expansion. How many terms are you going to get out of this expansion? This is what you get as a solution to that command. It is not a polynomial because it has this order term, and here is the order term. And so the cure for that is to convert it to a polynomial, just the way you would do it to a Taylor series. And this is what it looks like at that point. And we can see here x of tau tau. And tau is this expression times t. And if I am mispronouncing that Greek letter tau, please forgive me. Could be tau, it could be tau, I really don't know. I had a prof when I was a student, statistics prof, who used to pronounce the Greek letter mu. I guess we would say mu. He would pronounce it moo with a mischievous little smile because he knew that it was going to get everybody's attention. I had a Greek student at one point, an authentic Greek student. I asked him how to pronounce that letter. Is it mu or mu? And he looked at me and said, no, it's me. At which point I shrugged my shoulders and said, I don't know any of these letters. You hear different profs say different pronunciations. So you hear beta and beta. I don't know. So I'm going to call this guy Ta, and if I'm mispronouncing it, I would be happy to be corrected. Okay, so what are we looking at here? X of ta, not x of t, it's x of ta. And ta is this multiple of t. This down here is what I get when I make the substitution. And so this is now x of t. Notice it's a rather large expression because every place there was a ta, here and here, you have this large expression to put in. So what has happened here is the frequency has been expanded in powers of the parameter A, and that drags in the initial displacement. If you did not know what was going on here and you simply invoked this command and got this result, I believe you'd be left scratching your head saying what's going on here. So that's one of the things we want to talk about to illustrate what's really happening here. How did all of this stuff take place? Before we get into the details of how this expansion was created, let's just draw a couple of pictures. So right here we have a graph of this expression, which is the angular frequency, tau over t, and I've called that omega. It clearly depends on A, and I'm showing the dependence of of omega on A. It's quadratic, so because we've just got a squared here. Okay, and I have to fix a value of little a. Well, I fixed it at 0.6, and it's parabolic, right? So there is a dependence of the angular frequency on the initial displacement, capital A. And this is an animation of the solution x against t. And there are two parameters to play with. There is the value of the parameter little a, and there is the value of the initial displacement. And keep your eye on the shape of the graph, where it intersects the x-axis. As you change the initial displacement, you'll notice that the distance between these zeros changes, meaning that the frequency is going to depend on the value of that initial displacement A. So this is just some visual evidence of what we claimed. We have not really gone into the details of how we computed this, but just set the scene before we get into nitty gritty. This is what's really behind the difference between the linear and the nonlinear oscillator. Let's continue looking at these results for the nonlinear oscillator. Quick summary. This variable tau is omega t, and omega is expanded in a Taylor series, and it depends on the parameter a. So it would look like this times t. And then I thought I would do this numerical experiment. Let's solve the initial value problem numerically, and let's compare it to the Lindstedt approximation. And you'll see one is in black and one is in red, and the comparison on this range, 50 to 60, is pretty good. So you get further out with the Lindstedt approximation than you get with a regular approximation. Now there's another way we can look at the dependence of frequency on initial amplitude. We begin by getting a first integral. So we take the differential equation. Now I'm grabbing the left-hand side. The right-hand side is 0. You multiply through by x dot, and you integrate. Well, this is what you get on the left. But you're on the right, you would be integrating 0, so you would get a constant. So we begin with this result. This is the first integral. We want to evaluate this k. So we make things a little simpler here. We'll let x be u and x dot be v. And so it looks like this. And if we evaluate at the initial point, then the value of that constant, see, this becomes a, so you get a squared. This cosine little a, big A, and v was 0 at the initial point. So keep thinking about this. X dot we called v. Now if you isolate dt, it's dx over v. This goes up and this goes down. But x is u, so dt is du over v of u. So in other words, you can take this equation of this stuff equals this stuff and solve for v, because it's a u and there's a v. So you solve for v. Now here's the differential equation. X double dot is actually v dot, because v is the first derivative. X is u, x is u. Now evaluate this at the initial point and solve for v dot. So this was an a, and this was an a. So you got v dot equals sine little a big A minus a. Where are we going with this? This is an orbit in the phase plane. See, it's an implicit plot of the equation, first integral stuff with the value of the constant evaluated. And just to see that these closed curves persist, I made an explore. So you see you got these closed curves for the orbit. And what I really want is some way of determining the sign on v dot. So I took this stuff here and I graphed it as a function of little a and big A. And it appears that that quantity on this domain, 0 to 1, 0 to 1, is negative. So what does that tell you? It tells you that you sit right here, that's the initial point, u is a, v was 0, v dot is 0, so it's decreasing. So v is decreasing. So you're traversing the orbit in the clockwise direction. That's what I wanted to establish. Because if I solve for v, I get two solutions, plus and minus. And this analysis tells me I want this solution, this branch of the v. Now, I would like to know how long it takes to make one orbit. Okay? It's one period, one orbit. So I'm going to integrate on this piece and multiply by 4. So there's the multiply by 4. There's the integral. Starting from a, and I'll let a go to 0, so I'm going in this direction of this du over v of u, and it's this v that I want to integrate. And that tells me the time it takes, provided I got that multiplicative factor of 4. So this is the time it takes to go around once. And I want to go from that to omega. But this is a difficult integral to evaluate. So what I'm going to do is look at omega, angular frequency, which is 2 pi over the time. And expand that in the series. Well, I have to convert that to a polynomial because this will come out with a big O symbol on it. And there's omega. And I would like to compare that to what we got when we looked at the result from the perturbation method. We got a result that told us what the angular frequency should be, which is tau over t. This and this are the same except for the order in these two terms here. We now proceed to look at some of the theory behind this Lindstedt perturbation. Omega depends on A. It's expanded in a series. This is what the series looks like. It starts with 1. We change variables to tau, which is omega t. So t is tau over omega. X of t will therefore become a function of tau, and I will call that function of tau by the name u. And then we expand u of tau in a series with respect to a. Okay, so here's x of t becomes x of tau over omega, and we call that u of tau. And the expansion is in powers of a with coefficients functions of tau. You will need a chain rule here because we're changing variables in a differential equation. So dx dt is du d tau dt, and d tau dt is omega, and the u d tau I will call u prime. Second derivative just picks up another omega, so it's omega squared. differential equation now looks like this. Omega squared u double prime plus u minus sine of au. And this sine function is expanded in the Taylor series for a sine, and you get au minus au cubed over 3 factorial dot dot dot. And what does u look like for our purposes here? Remember, u is this series expansion, so I'm going to write it as these three terms, u0 up through u3 powers of a squared, a cubed. And we put this stuff back into the differential equation. There's your omega squared, u double prime. We take u to third order double prime. This is plus u minus au plus a cubed u cubed over 6. Let's look at omega squared. So let's take this omega, here's omega, and we're going to have to square that. And everything else stays the same for a moment. Here is the second derivative term, the u term, au term, u cubed term. This thing gets squared, and it will look like this. And I've just kept it out to a cubed. That multiplies the second derivative stuff. Here's u, au, u cubed. And as we've gone down here, you should have noticed that whenever I have a derivative on one of these subscripted or indexed u's, I put the index underneath. And the reason for that is that Maple still has not figured out how to put that index directly under the derivative sign. It will push one or the other off to the right. It drives me crazy. So I've tried a bunch of different things. I decided the thing that looked the best was to put the index underneath for those terms that have a derivative on them. So now you've got to multiply all of this stuff out here and begin collecting terms and get the coefficients of A0, A1, A2, A3, and you got to deal with this cube thing here. But because it's already multiplied by A cubed, you just stop and think for a minute. When you cube this out, you're going to get a U0 and an A1, U1. And you're going to get higher powers. But that's all multiplied by A cubed, and we're not carrying anything higher than A fourth. So we really only have to worry about these two terms. So when I start collecting terms, keep that in mind and begin getting the coefficient of A0, which is this, the coefficient of A1, which is that. I'm not going to drag you through the algebra. You can do the algebra if you like, but I will do the algebra eventually in Maple so that the bookkeeping comes out right. And there's the coefficient of the A squared term, and there's the coefficient of the A cubed term. We need to think about the initial conditions for this first differential equation, because you got to set all these coefficients equal to 0. For the first one, u of 0 is a, and for all the rest, you use inert initial conditions. We will now carry out these computations. At least this is a summary of those computations. They're clearly were done in Maple. The first term must be obtained from this initial value problem. Solution is a cos tau. The second term comes from this initial value problem, and you notice that you have u0 in that differential equation, but you now know u0, so the initial value problem has this differential equation. This is the solution. And if you notice, the solution has this secular term. And in order to get rid of that secular term, this coefficient must be 0. So 2 omega 1 plus 1 equals 0, or omega 1 is minus a half. Here is the expression for omega, and you can see the minus a half showing up here. The a squared term, well, there's u0 in it and u1 in it, and omega 1 is in it. And so you have to make these substitutions to get this differential equation in just u2. u2 will turn out to be this expression, and it's got a secular term in it. In order to get rid of that secular term, you make its coefficient 0. So 1 plus 8 omega 2 is 0, or omega 2 is minus 1/8. That's where this guy comes from. This is then the A3 term. This is the differential equation. There's omega 1, omega 2. There's a u0, there's a u1, which we have, and there's a u2, which we have, u0. So the differential equation becomes this, and here is the solution, and there is right here a secular term. So all of this stuff must be 0. That makes omega 3 turn out to be this. Therefore, this term is gone, and this is u3. This omega 3 shows up down here. We have put our solution, or obtained a solution, in this form, and then we stop and say, oh, but wait, Maple's by perturbation command put the solution in this form. So you have to compare. Take this stuff, which, see that over 192, that's this stuff, subtract this stuff. See, there's the 48. And if the difference simplifies to 0, then they're the same, and it is much easier to show two things are equivalent by showing the difference is 0 than it is to bludgeon one of these expressions into the other. That's just not fun to do in Maple. So if you were doing this computation, these are the calculations you would have to carry out. You would probably welcome a tool like Maple. I can't see doing things like this by hand. It's just so painful. Now I'm going to look at the stepwise solution that Maple provides via that by perturbation command. I think at this point it should be understandable. Now, the command is the same as I showed earlier, but I have modified it by this one extra option. this display style equals compact, which takes these annotations and moves them to the side instead of them being interlinear, which makes it, in my opinion, much harder to read. I have made the font a tad smaller because if I don't, this stuff will be pushed off the screen. But I think I'm going to ignore most of these comments. I'm just going to go through some of these steps. Here's a differential equation. Here's the initial data. This is the derivative condition equals 0. This has been expanded, and so you can see this pair of terms resulting from the expansion of the sign, and it's still a series data structure, and so there is the need to hit it with convert to polynomial, get rid of that big O symbol, because otherwise you can't work with this thing. So here's the differential equation. And the next thing you see is an expansion for x. All right, this is what x is expanded as. There is tau equals omega t, and there is the expansion for omega. And here you have this series data type, and you got to hit it with convert to polynomial. And then you make your substitutions. Here they're made before the conversion. So, differential equation in its series form. Here's where the chain rule takes place. You get powers of omega for each derivative. So now the differential equation becomes, as we saw, omega squared derivative, and here's omega squared derivative. This is not collected in any useful form, and it's still a series data type. Here is the first differential equation. Here is the first initial value problem. And I believe at this point, Maple spends too much time solving this simple initial value problem. It solves it from very, very basic first principles. And it takes all the way down to here to discover the solution. And when you put all of the comments in between all of these steps, it fills the page. I wish there were a way that one could group these or break this down somehow. And there is even a check on the validity of that solution. And so you get this. Okay, so now we're going back to the big messy differential equation and making the substitutions in that. So instead of collecting each differential equation that you need one after the other, it solves one, puts that information back in the big messy thing, and works with that. So here is the differential equation for x1. The driving term is collected this way. And here's the difference between what Maple does and the way I did it. Maple looks at this differential equation and says the driving term containing this cosine is going to generate a secular term. because it knows that here you're going to get a sine and a cosine, and this is going to give you a tau cosine. And so it eliminates that term by choice of omega 1 before it solves the equation. Solves the differential equation and applies the initial data. It discovers that x1 is 0. It takes that information, puts it back into that big messy expression for the differential equation, and it extracts the coefficient, the second order term. Notice that it relies on spotting that this cosine term on the right is going to generate the secular term. So instead of solving the equation and seeing the secular term, it says this will cause the secular term, and therefore its coefficient has to be 0, and that's where you get the omega 2 is 1/8. You take that information and you put it back into the big messy differential equation. That's right here, but before getting right here, Maple solves this initial value problem and simply declares x2 is 0. It did not go through all of the detail on solving that simple differential equation that it did earlier. It realized it's too tedious to do that. So now this is the big messy differential equation. You put all of this information into it, and you've got the third order coefficient. The third order coefficient is massaged into this form. This cosine is going to generate a secular term. This is cos 3t. It does not generate a secular term. And you see what's happened from here to here? This is a cosine cubed. This is a cosine 3 tau. There's trigonometry that took place between here and here. It could get by you if you're not paying really, really, really close attention. So this is where your secular term is going to come from. This coefficient has to be 0. That gives you the omega 3. You put that stuff, that information back in here. You have an initial value problem. You get an x3. This is what this solution looks like when this term drops out and this cos of 3 tau is converted to this bit of trigonometry. This is x of t, this was x of tau, this is x of t, with a substitution for what tau is, taken from here, and it shows up here, here, and here. My feeling is that a student who did not have a presentation of the Lindstedt method before trying to read the steps out of this solution might struggle. And therefore, I'm going to show a Maple solution one last time, and it is basically the solution that I put into my AEM book 25 years ago, because there was no Student ODEs package way back then. Let's look at this Maple command-based implementation. So here is the differential equation. Here is the expansion of omega as a function of a. You can see what that symbol represents. This is to change your variables. Use PDE tools. D change to change variables. T becomes tau over omega. This is the expansion of this sine term. And these expansions would pick up the order term, and this convert to polynomial removes that order term so you can continue working with these expressions. So the sine expands, you get these first two terms of the sine expansion. This is the representation, or the series representation, of the solution in terms of tau, so U0, U1, etc. You plug everything in, and you're going to get this big expression way up here to 8 to the 12th power. We don't need to go up that far. So one way to chop it down is through a series expansion of this expression. And again, you pick up an order term, so you convert to polynomial. If you go just up to 4, that's what the order term would contain. You just get a to the third power terms. And here's a way to pick out the individual expressions that are the coefficients of the powers of A. Use the coefficient command. Now start solving the initial value problems associated with each of these coefficients. So here's the first one. You use dsolve. Here's the initial conditions. You're solving for U0. This is what you discover, A cos tau. Now, to get U1, you need U0. So you've got to make a substitution. I use the val here to make that substitution. The initial conditions are now inert. You solve for U1, and this is what you get. So here's where I just go for the solution using dsolve rather than try to figure out which terms are going to give me the secular terms. And you can see that this is a secular term, so you want to set this coefficient to 0. So you pick off that coefficient and you solve for omega 1, and that causes U1 to be 0. Then you have to put that information into the differential equation for U2. Put that in, dsolve, you get this solution. It's again got a secular term, so you got to set this coefficient equal to 0, so pick off that coefficient, and it becomes 0 if omega 2 is minus 1/8. And that will cause, when you plug it back in, that will cause U2 also to be 0. So U1 and U2 are both 0. So you put all of that into the third powers equation and do a dsolve. And here's your solution. And you look in here and you say, oh, this sine times this t, this tau, is going to be a secular term. So let's pick out the coefficient of sine tau, and you get A tau and this stuff. And you make it 0 by choosing omega 3 correctly. So you solve that expression for omega 3. This will make this term be 0. You put that information back into this solution, and all that's left is this stuff, this part here. So add up the omegas and the powers of A. You get this expansion for omega. This set of substitutions gives you the approximation U of tau up to that third order in A. And if we look at the solution that we get by the Student ODEs command by perturbation, it would produce an order term, and I've removed it by the convert polynomial. You see here is the solution produced by this new command, and a quick glance here shows that these are the same, and here's tau. And if we create the solution from these bits by adding up the u's and adding up the omegas and getting the tau and getting x of t, this is the solution in t, and this is what we got earlier as the solution in t, and these two solutions agree, and we have, in a sense, closed the loop to do something two different ways and get to the same point.